In this lecture, we will learn about the thin films and coatings, how they are being applied on the surfaces of the bio implant devices and materials to enhance the cytocompatibility of all those devices once it is incorporated into the body. Generally, the bulk properties of the device materials, they are somehow designed to ensure proper design and fabrication of biomaterial devices for certain applications, certain properties such as appropriate mechanical properties. In terms of its durability, it can also incorporate the corrosion resistance and even the functionality of that particular device. So, the bulk properties dictate the appropriate mechanical response, chemical response and the biological response once they are inserted into the body. Such as hip implant, it has to withstand very high stresses, that is the structural requirement. Hemodialyzer, it requires very good permeability, and then again that is again a fabrication requirement. An artificial heart, it needs flexing for millions and millions of cycles. So, we can see a variety of such requirement by hip implant, hemodialyzer, heart implant. So, in terms of withstanding either high stresses or high permeability or even flexing for millions and millions of cycles. So, we can see the bulk properties are being dictated by the functionality or the properties of the material itself, the bulk the properties of the bulk material in it itself. But once it has to interface with the biological entity, the environment, it has to be incorporated with certain surface layer. So, in order that the overall bulk properties they are maintained, at the same time we enhance the interaction of this particular device with the surrounding material. So, that is the reason, that is the critical reason that we require thin films and coatings. So, this thin films and coatings, they can render biological response to biomaterials and devices while maintaining the mechanical and functionality of the device which has been now placed into the body. So, the thin films and device, they get dictated by the surface chemistry. So, the overall response of this device, it gets dictated by the surface chemistry and the structure. And the idea of applying this thin film coating to retain the key physical properties of the biomaterial, the bulk properties are now being maintained while modifying its bio interaction with the body. So, in the process what happens, we are applying thin films, it will retain the mechanical properties, they remain unaffected, but its interfacing with the tissues and the cells nearby, that is now being modified because of these thin films and coatings. So, we can see that thin films and coatings, they can render biological response to the biomaterials and the devices which are placed inside the body. They are dictated by surface chemistry and structure. So, we can somehow tailor the surface chemistry and the structure in order to curtail or enhance certain response of this device with the surrounding tissues. And in the process, it retains the key physical properties of the biomaterial. So, it does not affect the mechanical properties and the functionality, but it modifies only the bio interaction part. So, the thin films and coatings, they can render enhanced cytocompatibility. So, it can modify the biocompatibility while maintaining the mechanical properties of the device. Certain modifications are required, such as it can be surface modification. So, surface modification can include blood compatibility. So, in certain cases when we require the blood compatibility with the inserted device, we can utilize silicon containing block copolymer additives. So, or siloxane polymer deposition, chemically modified polystyrene and or plasma fluoropolymer deposition. So, these are certain materials which can be utilized for enhancing the blood compatibility with the device material. So, these are being applied as a coating onto a device material to enhance the overall interaction and without letting the blood clot or inducing thrombosis in those particular regions. Otherwise, device can induce certain toxicity, it can also encourage thrombosis near those regions where the device has been inserted. So, this induces the blood compatibility by certain materials such as silicon containing block copolymer, siloxanes or chemically modified polystyrene or even plasma fluoropolymer deposition. And in certain cases when we require cell adhesion and growth, so once we want the material, when the device is being inserted into the body and we want it to become an integral part of the of a particular organ itself, so it has now to be encompassed with the cell So, cell should adhere on the surface and they should just basically engulf the overall entire machine for a nice anchoring. So, cell adhesion and growth can be encouraged such as by oxidized polystyrene surface, ammonia plasma treated surface, or plasma deposited acetone film. These are all which are required for enhancing the cell adhesion and growth, but in certain cases when we want to reduce the overall interaction of those cells with the entity, because in that case we sometimes we want to remove that particular device or add something additional on the surface of the device, then we do not want cells to damage the surface of the device material, or if in case we want it to act as a sensor or retain there, so that we can analyze the chemical composition of the nearby blood or even the pH value. So, we want that particular surface to remain exposed for certain duration of time. So, we do not want the cells to grow onto that particular region. So, in those cases we want to reduce the cell adhesion on those surfaces, and we can utilize plasma fluoropolymer deposition again in certain cases. So, we can either utilize certain techniques or certain composites, certain materials to impart that particular effect. Again, the surface modification can also be required in terms of controlling the protein adsorption. So, if we want to incorporate or want to reduce the adsorption, we can impart immobilized polyethylene glycol. We can also impart ELISA dish surface to enhance the overall protein adsorption. Utilizing ELISA dish, there is nothing but enzyme linked immunosorbent assay. So, ELISA dish surface, it can impart enhanced protein adsorption. Again, once we start cross linking the contact lens, it can again reduce the overall protein adsorption, otherwise it will basically create a problem in terms of interlocking the surfaces, because once protein gets adsorbed, then only the cells start coming onto the surface and they adhere to the surface and get adsorbed. So, to eliminate the overall growth of cell or precipitation of certain cells on the surface of a device material, we want to control the protein adsorption, and that can be induced by surface cross linking such as for contact lenses. And in certain regions we want to improve the lubricity. In case once we have certain joints, we want to enhance the lubricity so that the mating surfaces do undergo the minimum friction. So, we can impart certain treatments such as plasma treatment. We can also induce radiation grafted hydrogels. We can also induce something called interpenetrating polymeric network in order to supply nutrients or even to supply the lubricants for reducing the overall friction between the two mating surfaces or adjoining surfaces. And in some cases we also want to enhance the life of the particular device or an implant. We also want to improve its wear resistance and the corrosion resistance. That can be achieved by ion implantation or even doing the anodization or diamond deposition. So, we can see either by diamond deposition or anodization, we can enhance the wear and corrosion resistance of the implant or the device material. And in certain cases we want to improve the transport properties in order to enhance the drug delivery or supply certain nutrients to a certain location. We can do plasma deposition of such as methane or siloxanes. In some cases we want to have electrical insulation, such as in the pumping heart region. So, in that case we want to when the leads are just coming out, we want to have them insulated so that they do not really short circuit. So, we can do something called plasma deposition. We can also apply solvent coatings, or we can also apply perylene insulation in those regimes. So, we can see we can apply certain techniques for either improving the wear resistance, corrosion resistance, improving the transport properties, even inducing lubricity or providing electrical insulation. So, these surface modifications become very critical in terms of dictating the functionality or the overall surface interaction of the device with the nearby tissues or the environment or even the fluid around it. And now there are certain techniques which can be utilized for modifying the surfaces of the biomaterials. So, once a biomaterial is being introduced into the body, the surface can be modified either by chemical or physical alteration of the surface. So, either we take the inserted surface of the implant material or the device material, we somehow change the chemistry of the top layer. In that particular manner, we are changing the chemical or physical nature of the surface of the implant directly. That can be done by either etching. So, we apply certain chemicals to it and then etch the surface to make it much more rougher. Chemical modification, again by changing the chemistry, by letting it react with some other species, or even roughening, so in order to enhance the surface area which comes in contact with the adjoining surfaces or the living environment. So, we can see that we can alter the surface of the device itself or the implant itself by altering its chemistry or by its physical nature. And there is second technique, we can somehow coat or allow some different material to get deposited on the surface of the implant material. So, we can either we can also overcoat the surface of the implant material or the device material via certain coatings or by implanting certain thin films or by grafting. So, we can see we can have two kind of techniques, either we can go by chemical or physical alteration of the surface, or we can also go by overcoating the surface, such as by coating or introducing thin films and grafting. So, there are certain techniques. So, if we have original surface, so we can see this original surface is now very much prone for things like corrosion, wear resistance, even the cytocompatibility can become an issue. It can also release certain ions, and if we want to impart certain functionality, if we want the tissues to get attracted, or even the blood, we want to introduce the blood compatibility. So, we need to somehow modify the surface accordingly. There are certain techniques. In first case, we can just overcoat the material. So, we have this original surface and we then overcoat it with certain material to impart that particular functionality. So, in this case, we can apply just some material which can protect this our underlying surface. This is nothing but the original surface and impart certain functionality. In certain cases, we can also introduce a gradient surface, because this surface might be very inert, and if we want to impart certain functionality to it, and say if we want to have much more cell compatibility of this surface, but we also want to have the interlayer to be very strong and adherent. So, we need to go gradually from this property of not allowing the cells to grow onto it to a very cell active surface, such as going from a very inert alumina surface, aluminum oxide, to a hydroxyapatite surface. So, aluminum oxide may provide much more toughening to it, but hydroxyapatite will provide much more cell activity on the surface. So, in that particular case, we want to go from 100% alumina to 100% hydroxyapatite. So, we have Al2O3 100%, and in this case we want to go for hydroxyapatite 100%. So, in this case we want to go gradually from 90, 80, 70, 60% of alumina to eventually come to 0% alumina. So, we are providing nothing but a gradient surface. So, that part also can be taken care by using certain surface modification, and we can also apply certain self assembled layers. These are called Langmuir-Bloggett self assembled layers. So, we can provide certain functionality to the surface. So, we can either impart we can let the polar head groups stick on the surface, and again, so that can basically stick to the fluidic region. So, polar head region will be much more hydrophilic in nature, whereas hydrophobic regions can stay outside, so that it will reduce the overall wetting of the surface. It can be done otherwise also. We can let the hydrophobic region get attracted on the surface, and then let hydrophilic region come on the top surface. So, we can apply this Langmuir-Bloggett self assembled layers for again imparting certain functionality. Then there is one more feature, we can also add something called surface active bulk additives. In this case, we add certain material in the bulk of this particular original surface, and we play with the interfacial energies of that particular additive, that it will have polar heads, it will also have certain tail region, and it happens that we can somehow make these particular bulk additives to come and sit on the surface just by playing with the interfacial energies of this additive and the original surface. So, it can that will be dictated by the overall difference between the interfacial energies of the additive and that of a bulk material, and the difference between the interfacial energy of this additive with air and difference between the interfacial energy of this additive with the substrate. So, it should feel much more stable once it is sitting on the surface. So, that interfacial energy has to be much lower than that of a additive and the substrate interfacial energy. So, so what we are doing, we are just reducing the overall energy of the system by letting the bulk additive come and sit on the surface. So, just by a single processing step, we can allow this particular additive to come on the surface and impart certain functionality to the original surface. We can also induce something called surface chemical reaction. So, once we have say OH group on the surface, we can make it react and make it a methyl CH3 group. So, from alcohol OH we can go to oxymethyl group on the surface to impart certain functionality. So, that is also possible by inducing surface chemical reaction, and we can also introduce reactivity by enhance the reactivity of the surface by roughening it or etching it. So, once we have the surface which was very smooth, and now we introduce surface roughness on the top of this particular surface, then we can still achieve enhanced functionality or enhanced surface area which is available for the reaction. So, we can see we have certain surface modification techniques. We can either overcoat, we can apply gradient layers, we can also apply Langmuir-Bloget layers for imparting certain functionality. We can add bulk additives to the surface, we can impart certain chemical reactions, or we can also enhance the surface activity by introducing roughness to the surface. So, we can see these surface modifications are now possible by these all techniques. And once we are coating a thin surface, we are targeting a monolayer of around 3 to 10 angstrom in thickness. And basically, to ensure complete coverage, we can go for up to 25 to 50 angstroms of Langmuir-Bloget films, because we do not want any part to remain unreacted or uncoated. So, in that case, we may want to go for 25 to 50 angstrom. But what happens as we go for thicker and thicker coatings, though we are ensuring the complete coverage, but now coatings become much prone to delamination, because as soon as coatings start becoming much thicker, it starts incorporating certain stresses, residual stresses, and that might lead to its breakage. So, minimal thickness of this particular coatings, they ensure uniformity, that it is nicely uniform, it is durable, and it is also highly functional. So, we can see the thin surfaces, they are basically targeted in the range of 3 to 10 angstroms, and to ensure the complete coverage, we might even go for 25 to 50 angstrom thicker layer, but thicker coatings have problem of getting delaminated or getting cracked. So, that is the reason we want to go for thin films, which basically ensure the durability, uniformity, and the good functionality of this particular surface. In order to reduce the overall delamination or enhance the resistance to delamination, what we can do, we can provide certain covalent binding of the modified region with the substrate. So, instead of only van der Waals forces or electrostatic forces to cover the surface, we can also impart certain chemical reactions and induce certain chemical or covalent bonds with the surface. So, we have surface bound with covalent bond to the applied coating, and then in the process it makes it much stronger. And we can also enhance the resistance to delamination by intermixing components. So, in first case we had substrate which was now chemically bound to the outside or the surface species. In this case, what we do intermixing the components of surface substrate and the surface films. So, in this case it is more like a gradient layer. So, we have this component, it has now good affinity with itself. So, we will provide some degree of bonding with the surface film. So, in this case we have substrate, and now the coating is approximately of the similar material, then we put one more layer, and then it is again of a different kind. So, but in the process what we are doing, we are intermixing the components, and by intermixing the components we are inducing some sort of a interaction between the substrate and the surface film. Third thing is, we can also introduce something called primer layer at the interface. Primer layer at the interface is again more like a glue, which can react again with the surface film to provide much more strengthening or resistance to delamination to the surface film. So, we can introduce primer layer at the interface to again impart resistance to delamination. Additionally, what we can do, we can also incorporate functional groups. So, if I have a particular layer, a particular substrate, we can impart certain functional groups which will bind strongly to the surface film. So, in the process, this functional group can impart much more stronger bonding with the surface layer to the substrate by acting as an interlayer. So, we can see there are so many techniques of improving the resistance to delamination. First, we can bind the surface layer covalently with the substrate. Secondly, we can also intermix the components of the surface and the substrate, or we can introduce something called primer layer to enhance the bonding, or we can also introduce something called functional groups to improve the bonding between the substrate and the surface layer. At the same time, once we are introducing a surface layer, we want to retain that particular surface rearrangement. If the surface starts getting rearranged, it might even break, it might lose the structure, it might lose the functionality as well. So, we want to retain the surface rearrangement the way we wanted or the way we had planned. So, first of all, we can reduce the movement or reduce the rearrangement part by cross linking the modified surface, or we can also sterically block the movement of surface. If we can allow, if we construct the chain in such a manner that it is not the overall movements are not possible sterically, the overall organization of the chain itself does not allow any further movement. So, in that particular way also we can somehow block the movement of surface. We can also introduce impermeable layer between the substrate and the surface. So, again we can impart a barrier between the substrate and the surface, so that the arrangement can be restricted. And again, after we have done all that, we also need to characterize the surface and ensure that the intended surface is really being formed. Otherwise, the overall device makes of no use, because we want to make sure that the intended surface is exactly it's really forming. It is not that it is getting rearranged to a different structure and getting damaged. So, we want to restrain the surface rearrangement, and that we can do by cross linking the surface, somehow sterically blocking the movement of surface structure. The arrangement of chain itself can be in such a manner that it does not allow any rearrangement, or also introducing something called impermeable layer between the substrate and the surface in order to minimize the movement. And after we have done that, we also should ensure that indeed intended surface is indeed being formed on the surface. And there are certain methods of surface modifications. So, we can see we can modify the surface by something called chemical reaction. So, in the chemical reaction what we can do, we can make the surface react with atoms or molecules at the surface. So, somehow we are now letting the surface atoms which are sitting on the surface of this particular device, let them react and then form something else. So, we had say OH group, we can make it react to form OHCH3, OCH3. In this case, it was much more hydrophilic in nature, and once we start introducing CH3, it becomes hydrophobic in nature. So, just by chemical reaction, we can change the overall contact angle on this particular surface. So, in this case, the contact angle will be much lower. In this case, contact angle of this thing will be very higher. So, we can see the contact angle is greater than 90 degree in this case. In this case, contact angle is much less than 90 degree. So, that can also be induced by utilizing chemical reactions. And again, the chemical reactions, they generally form monolayers. So, they do not overcoat with the reacting species. So, we do not want, if we are reacting it with certain species, we do not want it to settle down on this particular surface, but just form a single monolayer on the top of it, and they should not overcoat with the reacting species. Again, we can distribute different functional groups at surfaces. So, in some cases, if we want to have a surface which can take both hydrophilic as well as hydrophobic entities, we can impart functionality by introducing certain areas which will be specifically hydrophobic and other areas which will be specifically hydrophilic in nature. So, we can see these areas can be totally hydrophilic and other areas can be hydrophobic in nature. And if we introduce some surface, if we let any entity come over it, it will now be able to trap both hydrophilic as well as hydrophobic entities on its surface. So, we can impart biofunctionality to the surface by somehow distributing different functional groups at the surface. So, if water comes, OH will bind it. If any polar region or oleo group comes, CH3 might bind it. So, by chemical reactions, we can somehow react the atoms or the molecules which are sitting at the surface, and we can distribute different functionality by using these particular groups, but at the same time we form only monolayers and we do not overcoat with these particular reacting species. And there is additional method of modifying the surface is by radiation grafting. So, by in radiation grafting we utilize cobalt-60 and we impart UV radiation, and which is nothing but a very high energy or we also utilize very high energy electron beam. In the process they are doing nothing but breaking the chemical bonds. The bonding between the atoms or molecules can be easily disrupted by utilizing cobalt-60 or ultraviolet radiation or even using high energy electron beam. So, we can see we can somehow do the radiation grafting by breaking the bonding at the surface or by allowing either the cross linking or even cleaning the surface or even inducing sterility to the surface. We can utilize radiation grafting. So, in radiation grafting we can see it breaks the chemical bonds of the surface. So, whatever bonding is formed on the surface, whatever it be, it can start damaging the bond structure and it can basically break the chemical bond of the surface, and now that makes the surface highly reactive. Once the bonds have been broken, it makes the surface highly reactive, and all those reactive surfaces now can react with the free radicals. And if we introduce certain monomer, now the free radicals will now interact with the introduced monomer. So, in the process we are activating the surface by breaking the chemical bonds. They start reacting with a monomer which is now introduced in the system, and that now results in a very good bonding with the substrate. So, if you are able to activate the surface, let it react with the monomer, now it can bond very nicely or very strongly with the substrate. And again, by radiation grafting, as I said earlier, we can also control the ratio of hydrophilic or the hydrophobic ratio. It can be easily controlled. So, we can always say which kind of specific ratio of hydrophobicity to hydrophilicity we want to achieve in the system, and now we can make it react with specifically to a certain entity biologically. So, we can attract a particular biological species with a particular hydrophobicity to hydrophilicity ratio, and then that can be achieved by utilizing the radiation grafting, because we can control the overall radicals which are basically getting broken in the kind of monomer it is reacting with. So, we can control the hydrophilic and hydrophobic ratio. We can make a surface coated with something, and we can exactly control the regions where we are breaking the bonds by directing it, and once we have done that, we can let the monomer react to only those certain regions. So, in the process we have targeted the overall ratio of hydrophobic to hydrophilic content, and that is how we can really control the overall functionality or the reactivity of this system to the adjoining environment. Again, so in this process we can also see it can also bond hydrogels to hydrophobic polymers. So, we are seeing hydrogels, they contain much water, and hydrophobic polymers, they are basically repellent to waters. So, we can even achieve the bonding of these hydrogels to the hydrophobic polymers. So, that is again an advantage which we can achieve from the radiation grafting, because this can essentially be utilized to break the bonds and now control the exact reaction of that particular surface with any other chemical entity. It can be any monomer, and now we can change the overall functionality of that particular surface because of the radiation grafting, and we can even make hydrogels bond with the hydrophobic polymers. And then there is one more technique called radio frequency plasma deposition, and this is also called glow discharge. In this particular case, a low pressure ionized gas environment is maintained, and in this process we allow high radio frequency to generate ionized gas, and now it can modify the surfaces by either ablation or by etching, and also it can be utilized for depositions. So, in this case also we can either sterilize, we can either clean the surface, we can even sterilize it, or we can also utilize it for deposition. So, we can see that radio frequency plasma deposition is also called a glow discharge process. It can be utilized for cleaning the surface, even sterilizing the surface, or even depositing a different material onto its surface. So, it can easily modify the surfaces by either etching or ablation. What it does is it allows molecular diffusion to occur, and once molecular diffusion is occurring, it can allow the penetration of this particular chemical species to go onto the substrate. So, we have substrate, and this chemical entity now it can diffuse through the substrate as well, and once we have this sort of intermixing, it will lead to a very good adhesion. So, surface coating, whatever is getting deposited on the substrate, it can impart very good adhesion with the substrate material. One more advantage is that complex geometries can also be coated. It is basically doing nothing but we can also incorporate complex geometries, and also it is the coating itself is free of voids. It can have unique chemistry. It can also act as a very good barrier, and again it can be deposited on any surface. That is one more advantage of this radio frequency glow discharge, that we can utilize it for depositing it on any surface. And also this radio frequency plasma deposition, it also produces coatings which are sterile in nature. So, that is one more advantage of the radio frequency plasma deposition, that whatever coatings we are producing, they are sterile. So, that is the advantage of this radio frequency plasma deposition. So, in this case what we are doing, we are modifying the surface, we are also cleaning it, we can also etch or ablate the surface, we can also utilize it for deposition, and since it renders molecular diffusion, it can provide very good adhesion of the coating with the substrate. In this case we can allow very complex geometries to be incorporated, and since because of its high energy, it can render very coatings which are free of voids. They can have a very unique chemistry, they can also act as a good barrier films, and they can get deposited on any surface. And since it is utilizing again breaking the bond and utilizing radio frequency, the coatings which are produced, they are sterile, so they can be directly used in any biomedical application because they are already sterile in nature. So, that is the advantage of radio frequency plasma deposition. Now, there are certain kind of films which are called Langmuir-Bloggett films. So, in this case these basically form they are very highly ordered layer. So, in this case we introduce a particular fluid, then we deposit certain species to it, and they tend to arrange very systematically on the top surface of it. But in this case we need to keep the concentration of this particular species much below to that of a missile concentration. If it is above the missile concentration, then they tend to form missils. It means that all the polar head groups will combine as one, and the other hydrophilic tails will basically be protruding out. So, in order to maintain this particular geometries that they are aligned equi-spaced with each other, we need to keep the concentration very low. And in process what we can do, if we have some sort of a barrier layer and we start pushing this particular regime, we can control the overall distance between the chains, and in process we can also control the porosity, because porosity is nothing but the distance or the gap between the two. So, if we somehow compress them, we can reduce the porosity between them, and since it is nothing but the electrostatic attraction, we can they will tend to organize very near to each other. So, that is the reason it might imparted very high degree of uniformity. So, we can see that Langmuir-Bloggett film, they have a polar head and they have a non-polar head. So, polar head is basically out here and non-polar head is sitting on the top, and again it provides a high degree of order and uniformity, and again stability can be improved by cross linking. If we somehow cross-link all these chains with each other, we can improve its stability. And if you want to coat it, what we will do, we will just start pressing it and we will start lifting this particular substrate. So, in the process all these heads will start getting deposited. So, we will have this head which will start sitting onto its surface. So, we start just compressing it and lifting it, so that in process we can get a coating on this particular substrate. So, we have this substrate, and this is the overall coating which will form on the particular substrate. So, Langmuir-Bloggett films, they are highly ordered layers, they have polar heads plus non-polar regions. They can render very high degree of order and uniformity, and if we want to further improve its stability, we may just cross link all of them, and then it will result a very stable Langmuir-Bloggett film. There is also called something called self-assembled monolayers, and these monolayers, they get spontaneously formed as very high ordered structures. They have very strong exothermic adsorption once they start anchoring, and that provides the surface filling, because they make the surface very stable. So, as soon as a particular entity comes and sits, it will release certain heat, and this exothermic adsorption will now make them very stable. Again there is second order of attraction, that is called van der Waal attraction between those between all those alkyl chains, and as soon as they start coming together, it is better if they have some sort of attraction, and that makes them organize very strongly or very nicely and very nicely spaced and provide crystallinity as well. So, we can also get very good crystallinity if they have a very good van der Waal attraction which is existent between those particular chains. So, they can provide very good chemical stability as well. So, in the self assembled monolayer, it is more or less a chemical reaction what is happening on the surface, and they tend to form very high order structures because they can they can basically give out certain heat or exothermic adsorption. So, once they anchor, they release much energy and they can become much more stable. Secondly, the chains, they themselves can have some sort of van der Waal attraction of alkyl chains, and that brings them to much closer proximity and leads to the overall nice arrangement or or induces the crystallinity of the alkyl chains. So, once they have a good interaction between them, they can organize very nicely in very nice fashion, and it will lead to the crystallization of the alkyl chains, and in the process it can give it out very good chemical stability, both because of chemical bonding and secondly because of the van der Waal attraction force which is predominant between the alkyl chains. In the second category of the surface coating or inducing thin films, we have something called surface modifying additives. So, in this case we add low concentration of this particular material in bulk, which now emerges at the surface. So, such as in just to give an example, if we take a polyurethane matrix bulk and we have certain chains which have polyurethane head and PDMS chain group. So, we have polyurethane of a head, this material also is polyurethane. So, if we induce this particular material into the polyurethane matrix, we can expect polyurethane to have good compatibility with itself, polyurethane, whereas PDMS finds much more suitability once it is now being hanging outside in the air or with certain entity. So, we can see either it can get merged out here. So, this is nothing but PDMS, sorry, this one is polyurethane, which is the head groups are polyurethane and the tail groups are PDMS, which are just basically hanging out of the polyurethane matrix. So, now it can impart hydrophobicity to this particular surface. So, we can see polyurethane, it can now impart very high degree of hydrophobicity on the surface. So, in this case we can see we are adding PDMS in very low quantity in bulk, which now automatically emerges at the top or the surface, because now PDMS is a very high interface energy with that of a polyurethane. So, in process it will try to go to the surface and now form a surface with either air or the fluid around it. So, in that case it will try to reduce the interfacial energy, and in the process it will also impart certain functionality to the surface. And the mobility of additive in the bulk is decided by the overall rate of covering the surface and also the interfacial energy which is predominant between the polyurethane and the PDMS and the outside environment. And again the interfacial energy with additive must be higher. If it is not higher, then it will basically remain in the bulk and it will not come to the surface, so that the additive can be mobilized to reach the surface. So, in the particular example we have seen that polyurethane and PDMS, once they are inserted in a PU block, will bring PDMS on the surface. So, in the surface modifying additives, we add a particular entity in a lower concentration in bulk, and in process the overall interfacial energy of the additive must be higher, so that it can be mobilized to reach the surface and impart certain functionality. And the mobility of additive in bulk, that decides the overall rate of covering or coverage of the surface. If mobility of additive is very poor, the overall entire surface may not get covered properly. So, mobility of this particular entity is very slow. It might happen that only a few will be able to reach the surface and that is it will not cover the surface. But if the mobility of this particular additive is very high, then only it will be able to cover the entire surface completely, and that interfacial energy with the additive must be higher, so that the overall additive can be mobilized nicely and then it can cover the entire surface and impart certain functionality to the surface. A good example is polyurethane and PDMS combination. Once it is being inserted into the polyurethane block, it will bring the PDMS on the surface and will cover the entire surface. Again, there are some class of coatings which are called conversion coatings, and in conversion coatings we can somehow introduce the we can somehow oxidize the surface layer and surface layer of a metal, and we oxidize it and form a oxide rich layer. Such examples are titanium and aluminum. If we start oxidizing them, we can form TiO2 or Al2O3, and now these particular entities are very good in terms of inducing either adhesion, introducing lubricity, or providing corrosion resistance. And these coatings are generally transparent once very thin, up to 50 angstrom. They can be even made thicker, so up to even 5 micrometer. But as soon as we start increasing the thickness, it can even get damaged because of the stresses which are induced between the substrate and the generated coating. But in both the cases, titanium and aluminum, these coatings are pretty thin and they were adherent to the substrate surface. So we can see in conversion coating, we let a metal surface to get oxidized. So we form a very dense oxide, and dense oxide acts more like a barrier, and it imparts the resistance to the substrate material. It can also induce some lubricity by in this particular manner. It can also induce some sort of adhesion, and these coatings are generally transparent when they can be even between 50 angstroms or 5 nanometer to 5 micrometer in thickness. Then there is a last class of coatings which is called perylene coatings, and these are more or less like very good insulating coatings and moisture barrier. They have very good moisture barrier properties as well. What perylene coating involves is, it involves simultaneous vaporization, pyrolization and polymerization, and then deposition of this diaparaxylene. So we have this diaparaxylene, we do simultaneous vaporization, its pyrolization and its polymerization to finally deposit this particular coating, which are called perylene coatings, and they possess very good electrical insulation as well as good moisture barrier properties. So these are basically certain chemical coatings which are required to get which are basically deposited on the surface of a particular biomaterial or a device material. And again there is something called laser surface engineering. It utilizes laser, that is something called light amplification by stimulated emission of radiation. So we utilize laser for somehow engineering the surface, and the advantage of laser is we can precisely control the overall frequency, the density, the focusing and even the rastering. So we can select a particular regime with particular energy, with particular density, with a particular focus to impart certain functionality to the surface. So we can precisely control all these parameters of what all sort of energy we want to introduce, what all density we want to impart, whether it should be focused or defocused, or even how to raster or form certain geometries or certain surface topography. We can form certain surface contours to on this particular surface for providing certain functionality. And again, heating and excitation can be utilized to change. We can pulse the source and control the reaction time. So we can provide certain heating and excitation for changing the chemistry. We can also pulse the source and control the reaction time. So we can precisely see in what time this particular reaction will go to completion. So what all chemistries we want to retain on the surface, and what sort of functionality we want to provide to the surface. There are certain lasers which are very common, which are neodymium YAG, which is called yttrium, aluminum and garnet laser, argon laser and CO2 laser, and which are basically very commonly used. They also include annealing, etching, deposition and polymerization. So we can utilize laser for either annealing the surface, etching the surface out. So by etching we can provide certain contours and geometries to the particular material. We can also deposit certain materials or certain chemicals on the surface of the substrate. We can also induce cross linking or polymerization by utilizing lasers. So laser surface engineering has emerged as a wide tool in terms of precisely controlling the frequency, density, focus and rastering. So in that particular manner we can provide heating and excitation to the material for either changing the chemistry, for controlling the chemistry, for providing a particular reaction time. So, we can exactly control the overall chemicals which will be basically being retained on the surface, or the kind of reaction which should be is we should be able to control. So, the overall reaction time can be controlled. The degree of reaction can also be controlled by properly engineering the laser surface by engineering the laser, and there are certain lasers which are very common: neodymium, yttrium, aluminum garnet, aluminum and CO2 laser, carbon dioxide, and they include all these sort of things. We can anneal the surface to remove the certain surface stresses. We can etch the surface to provide much more physical area, or to enhance the activity by providing certain roughness to it. We can do deposition. So, we can provide any coating or any sort of surface action to it, and then we can also polymerize the surface, or we can also induce cross linking. So, in summary, we can see that the overall surface modification it becomes a must for retaining the bulk properties while rendering certain biological compatibility. So, surface modification is highly essential because we want to retain the bulk properties or the bulk mechanical and the functional properties, but rendering the surface or the biological compatibility becomes essential. So, we provide with a thin film coating or a grafting to improve the interaction of this particular device or implant material with the surrounding tissues or environment. So, in process we are enhancing the performance of this particular device or the implant material. It can be in terms of wear, corrosion. We can impart coatings of diamond, we can impart certain coatings, barrier coatings to improve the wear and corrosion resistance. We can also induce certain barrier performance. We can have some barrier layers. We can enhance the blood compatibility. We can also increase the permeability, such as in homodialysis. We want the oxygen to go through, but again the surface has to remain corrosion resistant. So, we can impart certain functionality or improve the performance by incorporating the surface coating, thin films and grafting. Again, we can provide these coatings or thin films by techniques such as radiation grafting. So, we can either utilize cobalt 60, UV radiation or electron beam radiation to control the overall structure. We can clean the surface, we can sterile the surface, or we can also do the deposition utilizing all these techniques. We also have plasma deposition, or also called the glow discharge technique. We can also utilize Langmuir blockade films. We can add surface additives which are incorporated into the bulk of the material, and they tend to come on the surface because of the mobility of this particular additive. Since the energy the interface energy of this additive is much higher with the bulk material, so it can have certain mobility and it can come on the surface and impart certain functionality. Then we have self assembled monolayers. We can also have conversion coatings, and we can also have laser surfacing. So, in the process we are allowing the chemical species to come, interact the surface and provide a very good bonding, while also inducing some sort of a interaction, electrostatic interaction between the chains to stabilize the surface coatings and make it very stable. We can have conversion coatings in which we can allow the oxidation of the surface, metallic surface, and induce much more corrosion resistance or a barrier nature of the film, even impart lubricity. And again we can have laser surfacing or laser engineering to coat a particular surface and somehow control the cross linking or polymerization of the surface and retain or provide certain gradient in terms of the overall functionality. It can be hydrophobicity, hydrophilicity, or even certain barrier nature, corrosion resistance, even deposition of the films. So, in the process we realize that how important is the surface coating or thin films or grafting to impart the interaction between the device and implant material with the surrounding body without hampering the overall mechanical functionality of the device or the implant material. Thank you.